Welcome to lecture 6 of our course on embedded sensing, actuation and interfacing systems. So, in today's lecture we will discuss about motion sensors and its interfacing aspects. Quickly recapping the last class activity. In the last lecture we have discussed on the temperature sensors and its interfacing circuits, where we have learnt about the RTD, thermistor, thermocouple and PN junction type sensor. So, these 4 type temperature sensor along with their interfacing circuits we have discussed. So, in today's topic we will discuss on motion sensors and its interfacing aspects. So, under motion sensors we will primarily discuss about the potentiometer, LVDT and accelerometer. So, let us start our today's session. Motion sensor. So, basically these motion sensors are used to monitor or measure various motion parameter of different system. For example, if we want to monitor or measure the displacement or position, then accelerations, angular velocity. So, these parameters will come under the motion, and the sensors which will be used for measurement of these parameters, so they will be called as the motion sensor, right. Now, let us see what are the transduction mechanisms are available. So, essentially what do we mean by transduction mechanism? So, suppose that motion, so either it is displacement or angular velocity or accelerations. So, these are essentially mechanical quantity, is not it? Now, as we told earlier that whatever be the physical parameter we want to measure, ultimately we have to convert it into some electrical quantity or more precisely voltage or current form, and then it needs to be further converted into digital signal, right. So, how to convert this mechanical quantity or parameters into the electrical domain? Either we can take help of some resistive mechanisms or some capacitive technique, or we can go for the inductive technique, right, because you know R, L and C, these are the 3 electrical quantity. So, using either of these 3 we can convert any physical parameter into the corresponding electrical quantity, right. So, the popular sensors which comes under the motion sensor, they are like potentiometer used for measurement of displacement. Then we have the LVDT, that is also used for measurement of displacement. Then we have the RVDT, which is used for sensing of basically this angular, so that LVDT, that is for linear position, and this RVDT for the angular position. And then we have the accelerometer for sensing accelerations, then we have the gyroscope for sensing the angular velocity and so on, right. So, just first let us start with the potentiometer. Okay. So, potentiometer is typically a 3-terminal device, and as we can see, so here this one is your potentiometer, and this is one terminal that we connect to the supply voltage. Then another terminal we can typically connect to the ground, and another we have the mid terminal, that is called as the wiper. Okay. So, this particular device is used for measurement of linear displacement. So, suppose let us consider this one is the object whose displacement I want to measure. So, then what I need to do? I will be just connecting this particular object to the wiper, and when this particular object will be moving, so then since the wiper is connected to the object, so that wiper will be also slided across its length, is not it? And essentially this particular potentiometer is resistive element. So, if I consider that suppose the total resistance, if I consider the total length is the L and total resistance if I consider as R, so then I can consider that per unit length what will be the resistance? Per unit length I can consider the resistance is simply R by L, is not it? Because your R is the total resistance, that is the R. So, if my total resistance is R, then per unit length the resistance will be R by L, right? And since this object is connected to the wiper and depending on the object movement the wiper will be sliding across its length. So essentially I can understand my x will vary depending on the object movement, is not it? And now this particular device, what it does, depending on the applied movement, what will happen, the slider position will change, and if I measure the voltage across these 2 points, so then obviously the effective resistance will change, and as a result the output voltage will also change, because this is simply acting as the voltage divider configuration. So if I have the supply voltage Vs, this one is the ground, and this, if I measure the voltage V0 across this mid terminal and this terminal, so then effectively depending on the applied displacement of the object, my resistance will change across these 2 terminal, and as a result the output voltage will also change, is not it? So suppose if I just give the name as A, this if I give the name as B, and this if I give the name as C, so then the output voltage V0, that I can simply write as RBC, that is the resistance across BC, divided by RAC, is not it? That is the total resistance. So what is my RBC? RBC is, I know that per unit length my resistance is R by L, is not it? So for X displacement, if I assume that displacement is X with respect to this C terminal, so then R by L into X divided by, what is your RAC? RAC is the total resistance R, is not it? So essentially what I can get, V0 I will be getting as simply X by L, and obviously here that Vs will be there because Vs is your supply voltage. So Vs will be multiplied, so X by L into Vs, is not it? Now since in this potentiometer my Vs is the supply voltage that is known to me, L is also the total length of the wire, that is also known. So from there simply I can tell my V0 will be proportional to X, that is the displacement, right? So in this way this simply potentiometer, this simple element or this device can be used for measurement of the displacement of any object, right? So essentially you can understand that for in this case we are considering about this linear displacement, is not it? This X is linearly it is moving. Now if I have some angular movement, so then there is some this kind of potentiometer is also available, where suppose these are the 3 terminal A, C, and suppose this one is the wiper terminal B, right? So that kind of potentiometer is also there. So where in this case this potentiometer length is, instead of linear straight line, its shape will be arc shaped, and depending on this movement of the object, so the object which will be moving like this with some angle, so the angle will be moving, and basically if I consider this angle as theta, so in this case the theta will vary, right? And based on similar analogy, in this case my output voltage will be proportional to theta. In the same way I can calculate, suppose if I consider the total arc angle is theta total and total resistance is R, so then per unit angle the resistance will be R by theta t, is not it? R by theta t. Then if I have some displacement theta, so then R by theta t multiplied by theta, that will be my resistance across this B and C. So suppose if this I consider, suppose this one is your theta, and if I then in that case my RBC, this resistance will be simply R by theta t into theta, is not it? And total resistance is R, so in that case my V output will be simply RR will get cancelled out, and I will be getting V0 is proportional to theta, is not it? So in this way I can use my potentiometer. For this potentiometer can be used for linear displacement measurement, and this kind of potentiometer can be used for the angular displacement measurement, right? So now let us move forward to the next sensor, where we will discuss about this linear variable differential transformer, that is the LVDT. That is again another one of the most important type displacement sensor, and it is having huge popularity in various embedded application, right? So this from the name itself what I can understand, linear variable differential transformer. So what do they mean? Linear means obviously that input output characteristics will be linear. Variable means with respect, if I vary the displacement, then it will produce you the electrical output voltage. Now differential transformer. So its construction is kind of transformer, and it is not the straightforward simple transformer, it is differential transformer. So that is the interpretations of this or the meaning of each of the term, that is linear, variable, differential transformer, and it typically looks like this kind of device. Okay. Now let us go through how the typical constructions of LVDT looks like. So it typically consists of one primary coil and two secondary coil. In normally we know in transformer we have one primary coil, one secondary coil, but in case of LVDT we have one primary excitation coil, that is this one is the primary excitation coil, and here we have the two secondary coils. Okay. Then it and obviously in between we have one this core, and that core will be movable. Okay. So this there will be a former in which this one primary coil and two secondary coils will be wrapped around, and primary coil will be in the middle position and two secondary coils will be in the either side of this primary excitation coil, and there will be one core. So this particular core will be of course made of some ferromagnetic material, so that depending on the core position, the that voltage will be induced in the two secondary pickup coil. Okay, because in the transformer principle we know in the primary coil we apply the excitation voltage, and then across the two secondary coil we take the measurement, is not it? So here we apply the input voltage, and across this two secondary coil, basically that depending on the core position, the flux cutting or the corresponding induced voltage will change in these two secondary coils, and then we will take the output voltage from the secondary coils. Now in this case the secondary coils, they are connected in a particular fashion, that is called as the series opposition. So the two secondary coils, they are connected in series opposition, and we will shortly know that why this particular series opposition is used. Okay. So this is the typical constructions. And now let us understand the working principle of the LVDT. So obviously one thing we can understand that in case of potentiometer, as we said, that basically the wiper or the mid terminal that is connected to my object, and when the object is moving, then my this wiper terminal was also moving, and accordingly my output voltage is changing. In this case what is happening, in this I will connect my movable object to this core. So basically suppose here if I have my movable object, so then that movable object will be connected to the core, and depending on the object position or movement of the object, this core will be moving, and depending on the core positions, my flux cutting or the induced voltage in the two secondary coils, they will vary, right? So now let us proceed further. So the working principle is, when an AC signal is applied to the primary excitation coil, so obviously voltage will be induced in two secondary pickup coils, and obviously the flux cutting will be through the ferromagnetic core, is not it? Now if the movable core is at center position means if it is equispaced from both the secondary coils, then what will happen essentially, in both the secondary coils equal voltage will be induced. And now if they are connected in series opposition, then obviously what will be my output voltage if the core is at center position? 0, is not it? Because in that case, if the core is at central positions, that means equispaced from both the secondary coils, then essentially in both the secondary coils equal voltage will be induced, and since they are connected in series opposition, so that's why if I take the difference of those two secondary coil output voltage, then obviously I will get 0. Then if my core position changes, so then I will get some non-zero output voltage depending on the position of the core, right? So let us understand this working principle with the help of this schematic diagram more properly. So suppose here you can understand that so suppose this is your primary coil, okay, here V in, that is the excitation voltage I have applied over here, and these are the two secondary coils S1 and S2, and you can see they are connected in series opposition. Okay, so this one is connected to this terminal, and I am taking the output voltage across this terminal and this terminal, right. Now this one is the movable core which is connected to the object whose displacement I want to measure, right. So this core will be connected to the object. Now suppose when this core is, as I said, equispaced for with respect to both the secondary coils, then as we said, in that case ES1 and ES2 both will be equal, and if I take the difference ES1 minus ES2, I will simply get 0. So just let us see. So suppose if I consider this is my primary, this is my input V in, okay, versus T. Now if I consider that the core is at central position, so then what I will get, if the core is at central position, so then both ES1, so this one will be your ES1 and this one will be your ES2, okay, this is your ES2. And if I consider, suppose if I consider this, that the total length, if I consider the total length as L, so then I can divide this L as 0, L by 2 and L in this 3 position. So when X equals to L by 2 at that position, that means the core is at central position, so then both ES1 and ES2 both are equal. So my output voltage E out, that is nothing but ES1 minus ES2, that will be simply 0, is not it? Now if I consider that X is between L by 2 to L, if X is between L by 2 to L, so then what will happen? If I consider that this core is towards S1, so then for the same V in, what I can get, this will be your, suppose ES1 when X is between L by 2 and L, and my ES2 value will be something like this, is not it? Because if the core is towards S1, so if it is moved upwards and if it is close to S1, so then obviously the coupling with respect to S1 will be more than S2, and as a result my ES1 value will be more than ES2, is not it? So if this one is my ES1, so if this one is the ES2, so then if I take the difference, that is ES1 minus ES2, so that will be obviously something like this. So this one is your E out. Fine. Now if my X is between 0 and L2, if X is between 0 and L by 2, that means if X is towards S2, then what will happen? Then if I consider this one is my ES1 and then this one is your ES2, and then if I take the difference, that means if this one is ES, and in this case my ES2 will be greater than ES1, so if I draw the E out, so then this, if I ES1 minus ES2 means there will be the phase difference. Right. So basically this what we can consider that if the core is towards S1, then coupling with respect to S1 will be more than S2, and as a result the E output will look like this one, Whereas if the core position is towards S2, then coupling with respect to S2 will be more, and in this case my output voltage will be like this, right. So what is the difference between these two output voltage? They are out of phase, is not it? Their phase are opposite to each other. If I consider that equal amount of amplitude, I am suppose that in the towards S1 I have moved x1, and towards this S2 if I move that minus x1 if I consider, so then the amplitude may be same, but what is the difference? The difference will be with respect to the phase characteristic, is not it? Because as we know that displacement is a vector quantity which is having both, it has magnitude as well as the direction, is not it? So that's why in this way, if the core is at mid positions, I will get output 0. If it is that towards S1, I will get positive output. If it is towards S2, I will get negative output. With this, that is basically the phase difference I will get, is not it? So as we said that if the core is displaced toward one end, one pickup coil will have more coupling than the other with the excitation coil, and thus produce larger output voltage which is proportional to displacement, and this differential output that will provide the measurement of my displacement, right. So one thing is clear that if I want to measure the displacement properly, then I need to measure both the magnitude or amplitude of the displacement as well as the direction of the displacement, is not it? Because the displacement is a vector quantity. So how to do that, those aspects we will shortly see. Now what are the salient features of LVDT? It is having very high accuracy, linearity is also very high, no wear and tear loss. This is again another important point. You remember when we discussed that potentiometer few minutes back, so then what we said that the wiper, if you see quickly, the wiper was actually slided across the length of the potentiometer, is not it? And depending on the object movement, the sliding will also happen. So essentially in this case, the wiper is in direct contact with your potentiometer, and if it is in direct contact, then what will happen? You will be getting wear and tear loss. So essentially your overall longevity or lifetime will be reduced. But in case of LVDT, that is not going to happen, because in this case you can understand there is no physical contact between the core and the coils. There is no physical contact, right. So they are basically electrically isolated, and also that through the magnetic coupling the induced EMF is happening, is not it? So that's why we are getting that no wear and tear loss, good lifetime, electrically isolated output. So these are some of the important benefits we can achieve from this LVDT. Typical range for LVDT is in the range of plus minus 0.25 millimeter to plus minus 25 centimeter, and maximum linearity is hardly plus minus 1% of full scale division. Okay. So these are typical features of the LVDT. Now let us move forward to understand its characteristics and interfacing aspect. So just we told that in order to measure the displacement properly, we need to know both the amplitude as well as the direction. So we should be able to distinguish between the positive and negative displacement properly, then only I can get, or I can basically measure the displacement properly, is not it? And for that we need suitable dedicated interfacing circuit, right. Let us see what are the circuits required over here. In order to achieve this directional sensitivity measurement, we have to use phase sensitive detector. That is one of the most important signal conditioning element for LVDT, is not it? And of course the low pass filter is required to smoothen the output and to get the DC output. Now let us look how the typical operations happens over here. So suppose here that further equivalent diagrams are shown over here. So this is your primary coil, and these are the two secondary coils. They are connected in series oppositions, and from here I am getting the output voltage, right. So if I compare the output and input, the frequency is same, but the phase difference will be there. As we we have seen just few minutes back that if I have if the core position is towards S1, then I will get the input and output are same phase. But if the core is towards S2, then if I compare the input and output, they are out of phase, right? So if I look at any AC waveform, in some oscilloscope or some waveform measurement device, so then you cannot distinguish by looking only at the waveforms, you cannot understand what is the phase, right? Because in both the cases it will be looking like this kind of sinusoidal thing, is not it? In order to distinguish the phase, you have to compare between two signals, then you can understand. But by looking at only one waveforms, you cannot tell whether this is in phase or out of phase, or what is the phase measurement over here, right? So that's why what we do, this output voltage is fed to the phase sensitive detector, and then further it is passed through one low pass filter, so that finally I will get the DC output voltage, right? So if I look at the characteristics, normally you can consider, suppose as I said that suppose this is the displacement, x axis is displacement and y axis is your voltage, and now if I look at only the AC amplitude, if I take the mod value of this output, that output mod value if I consider, so then this will be your corresponding AC characteristic, is not it? So this is your corresponding AC characteristics with respect to the displacement. If the displacement is, so I am considering this one is L by 2, so this I can consider as the positive displacement, and this is 0 to L by 2, this side I can consider as the negative displacement. In both the side, that mod amplitude will be same, so this will be called as the AC characteristics, and by looking at the AC characteristics, I cannot distinguish or identify whether the displacement is positive or negative. The amplitude I can know, but the directions I cannot know, right? So that's why I need to know about the DC characteristics. How we will get that? Through this phase sensitive detector and low pass filter. When this output is passed through this phase sensitive detector and low pass filter, so then I will get the output is like this. So this is corresponding to your DC characteristic, okay, where for positive displacement I will get plus VDC, and for negative displacement I will get minus PDC. And how I can do that? Obviously I have to determine the phase, right? Because you can see this phase, this is in phase when the displacement is positive, so this is in phase, and then when the displacement is negative, so then I am getting the phase difference as minus 180 degree. So these things I can achieve only through this phase sensitive detector, or it is called as the phase sensitive demodulator also, and then when I pass it through the low pass filter, I get the final DC output, right? So typically this phase sensitivity detector, you can understand, you take help of some that bridge rectifier circuits, or you can consider some kind of that digital gates as well for identifying the phase, and there are different kind of phase sensitive detector circuits are there which you can use it for this particular application, right? So that's why this AC and DC characteristics are also very important. Now next one is the RVDT. So as I said, this LVDT, that is used for measurement of linear displacement, is not it? Because in this case my core is moving linearly. Now similar to this potentiometer, as we said that for potentiometer I can, if I want to measure it some angular displacement, so then that linear potentiometer I cannot use, I have to use that arc shaped potentiometer, is not it? Similarly for RVDT, that for LVDT also, if I want to measure the angular displacement, then I have to use the RVDT, that means rotary variable differential transformer, right? So if I look at the construction between LVDT and RVDT, they are almost similar, only difference is with respect to the core shape. With respect to the core shape, there is difference between LVDT and RVDT, right? So let us see how the RVDT looks like. Yeah, and one small point over here, that in this case of this DC-AC characteristics, so obviously that beyond this range you can consider that is the characteristics is kind of saturating, right? That is because of the magnetic saturation, and also we have the maximum range between 0 to L, right? Okay. Okay, just coming back to this RBDT. So if I look at the RBDT construction, as you can see, this is your primary side and this is your secondary side, same, it is connected in the series opposition. You can look at the beautiful core over here. The core shape and dimensions are quite different, is not it? Why it is different? Because in case of a RBDT, I need to measure some angular displacement. So here you can consider this, this is connected to my some shaft which is actually moving at some plus minus theta angle, right? And depending on that, my core will be also moving at either clockwise or anti-clockwise, right? Either clockwise or anti-clockwise, the core will be also moving. And in both the cases, when it is clockwise, so in one coil it will be that close to one coil, one secondary coil. If it is anti-clockwise, then it will be close to another secondary coil, and as a result, if you take the that output differential output voltage, so then in one case you will be getting the in phase output with respect to the input, and another case you will be getting the out of phase output response with respect to the input signal, is not it? Similar characteristics like our LVDT, but only difference is with respect to the core position, core shape and dimension. Fine. Now let us look at what are the important applications of these position sensors, including your potentiometer, LVDT and RVDT. We can use it widely for various industrial control application. Then we have the flight control actuation purpose. We have the engine fuel control actuations, we can use it. Then we have various robotics application, and also we can use it for indirect pressure measurement. How we can do that? You remember that in the previous class we have discussed about some pressure sensor diaphragm element we have discussed, and we told the diaphragm was the primary sensing element, and in order to convert that position into resistance, we have connected some strain gauge on the diaphragm, and then the diaphragm, that strain gauge resistance was changing because of the applied strain, and in that way, in that pressure sensor we have used two elements. One was the primary diaphragm, that is the primary sensing element, and another was the strain gauge, that is the secondary sensing element, which was used to convert the displacement into resistance. Now if we don't use strain gauge, then what I can do, I can simply connect my, suppose if I have some diaphragm, or suppose there is some another type of pressure sensor that is called as the bellow. So when the pressure is applied, it gets deflected. So what we can do, this diaphragm or this bellow, that I can connect to the core of the LVDT, and due to pressure what will happen, this bellow or the diaphragm displacement will change, and that displacement will be converted into voltage using this LVDT, where this diaphragm or the bellow we are connecting to the core of the LVDT, and in that way this LVDT can be used as the secondary sensing element for pressure measurement as well, right? So this is about our that LVDT, RVDT and the potentiometer. Now let us move forward to the next sensor, which is the accelerometer, which will be used for measurement of vibration or acceleration, right? What is the typical mechanical model? This is the equivalent mechanical model can be considered as simple mass spring damper system, where I can consider a seismic mass will be connected to that vibrating object through the spring and the damper, right? And how will it work? So when typically you can consider this is suppose this is your vibrating object and this is your accelerometer sensor. Now when this vibrating object will be having some input excitation vibration, so then if I consider that one as something x1, and if I consider some resulting force F, so then what will happen, this accelerometer is mounted on this vibrating object, and depending on the accelerations or the vibrations, there will be that inside this accelerometer sensor, this mass spring damper systems will be having movement, is not it? So if I consider my F is the force which is coming from the vibrating object, and I can easily consider F is equals to simply mass into acceleration, that mass is mass m, and A is the applied acceleration input. So then because of this ma accelerations, that A accelerations, we have the resulting force of F, and because of that what will happen, this mass spring damper systems will be exhibiting some change in displacement. Displacement of what? Displacement of the seismic mass, is not it? So, in this case, when the accelerations or the vibrations will be applied to this acceleration sensor, then you can understand that x is the resulting displacement of the mass, and because of that displacement I will be having 3 more forces. One is the spring restoration force, that is simply k into x, right? Then you have the damper force, that is b into x dot, and one more force we will be having, that is your inertial force mx double dot. So now if I draw the free body diagram with respect to this mass of this acceleration sensor, so then this is your ma acceleration, that is the ma force, that is your input, right? And the corresponding other force which will be acting on the mass, they are the spring restoration force, damper force and the inertial force, and they will be acting opposite to the input force. And if I write the mass balance equations, so then simply mx double dot plus bx dot plus kx, that will be equal to your ma, is not it? So this is the equivalent that mathematical model for your mass spring damper systems or the acceleration sensor, where a is the input acceleration, and because of this a input acceleration, what is your resulting output? The resulting raw output is your x, that is the displacement, is not it? Because the accelerometer is connected to your vibrating object, and when it will be vibrating there will be relative displacement, and as a result, as we have seen, there will be 3 forces, that is the spring force, damper force and the inertial force, which will be acting together and they will counterbalance to the input force, and then this will be the resulting dynamic equations for your acceleration sensor, is not it? Now the acceleration is the input and x is the output. Now if you can measure this x, so from there you can easily calculate your acceleration input, is not it? Now how to measure this x? So x is again displacement, and already we have discussed that how to measure some displacement. So what we can do? With respect to this mass spring damper system, that is the accelerometer, you will be using some transduction mechanism, either some resistive or capacitive or piezoelectric, through which you will convert this displacement into corresponding voltage output, and by measuring that voltage you will get the measurement of your unknown applied acceleration, is not it? So that is the main fundamental principle of your accelerometer, right? And you remember that when we discussed about the dynamic characteristics of the sensors, we have discussed about this equation. So simply if I take the Laplace transform delta x by delta a in S domain, Laplace domain, I will be getting this transfer function where omega n is given as root k by m, that is the natural frequency of the sensor, and zeta is your damping ratio, is not it? So and k is your static sensitivity we can consider. So these are the basic mathematical model for our accelerometer. And as I said, this displacement has to be converted into voltage, either capacitive or resistive or piezoelectric mechanism, and depending on that I have different variation of accelerometer, capacitive accelerometer, resistive accelerometer, piezoelectric accelerometer, and so on, fine. And this is, we discussed about the single axis accelerometer. Similarly we have 2 axis and 3 axis accelerometer as well, and they are mostly manufactured using the micro machining technology, and that we will be discussing in later on modules in detail, okay. So what are the major applications of accelerometers? We can find its application in automotive, like for monitoring vehicle tilting, skidding, anti-lock braking system, in airbag deployment system, already we discussed earlier about this airbag application. Then we have this aerospace applications where we can use it for inertial navigations. Then we have the sports or gaming application to monitor the athlete performance. Then we have our personal gadgets like cell phone, digital device, and finally we have the industrial, robotics, and various kind of applications, right? So with this we have understood about the measurement of few motion parameters like positions, that under that we have discussed about this linear positions as well as the angular positions, and then also we have discussed about the acceleration measurement, right? So with this we are concluding our session for today. These are some of the references. Thank you.